And we're going to look at a prime example of an exponential function that everyone should know about, because everyone at some point will have to deal with a bank, right? So you either put money in the bank and they give you interest, or you borrow money and they charge you interest. So we want to know a little bit about interest. You would not know what interest is? So let's say you go to the bank and you want to put in $1,000. And they say, well, we'll give you 5% interest for, as you say in math, 0.05. And we'll give that to you at the end of the year. That's the term, or the compounding term. So let's figure this out. So we have $1,000, and we multiply it by 0.05. That's our interest. But we still have $1,000, right? So now, at the end of the year, we have 1,000 plus 1,000 times 0.05, or factoring to 1,000 times 1 plus 0.05. That's at the end of 1 year. But at the end of 2 years, I could just, now I have $1,050. I could just multiply that by 1.05 to see how much I have at the end of 2 years, or 3 years, or 4 years, and so forth. So really, I have an exponential function here. 1,000 times 1 plus 0.05 to the t, in this case t in years. All right, well that's the basics. Now we want to get a little more complicated, because your bank, they might give you a yearly interest rate, compounded yearly, but more likely they're going to compound it more often. You might compound it monthly, or even daily, or you might see something, you might say continuously. We'll have to see what that means in a minute, a few minutes. Okay, so this is yearly. How would I change this if it's monthly? Well, they're still going to give me a yearly interest rate. They're not going to change that. But the interest rate for a month is going to be 0.05 divided by 12. So we have to change this to 12. But if we wanted to know how much we're going to have at the end of the year, we have to raise this to the 12th. In other words, every month we multiply what we have by 1.1 plus 0.05 divided by 12. That's a little better than compounding yearly. I make a little more interest that way because we get interest on our interest. Okay, and then, per year, we just multiply it again by the number of years. That way, every year, 12 times a year, we increase how much we have. We go to daily. Now, what's changing here, right? Well, I say 1 plus 0.05 over n, raised to the n t. Well, that's how much interest I make given n is a number like 12 for monthly, or 365 for daily. And we could just take out the yearly interest rate here and put in I. And we could take out the initial principal. We could call that our initial principal. And we could just say this is the future principal as a function of t, where t is in years. So this is clearly an exponential function. Now, we'll get into the details in a bit, but what continuously means is we look at this expression and we take the n and we make it bigger and bigger and bigger. And you might think that that would mean that all of a sudden our money's going to, infinitely it's going to be compounded, it's going to become infinite, but no, we're going to do it compounded infinitely, but our interest rate keeps getting, the amount of interest per period keeps getting smaller. So let's see how that would actually work with a real problem. Let's go back to our we'll use our formula, but we'll use the numbers we were talking about. So we want to know how much we're going to have in 10 years. If we start with $1,000 and we get yearly interest, so it's I over 1 times 1 times the number of years, which is 10 years, right? And I, we're just going to use 5%. So that comes out to about $1,628.89. All right, so that's good. We put away our $1,000 for 10 years, and it didn't double, but it went up 60%, 5%. That's not bad. At some point in the 80s, when Jimmy Carter was president, we had this hyperinflation, and you could get 11, 12, even 15% on your money. Sounds good, except inflation was going up very quickly too. Nowadays, you'd be lucky to get 5%, right? Probably have to lock your money up for like 20 years to get 5%. If you just go to the bank and you want to be able to take your money out whenever you want, you won't even get 1%. So that changes. That's an economic thing. This isn't an economics class, so I'm not going to go any further. Okay, so what if we instead we put this money away, but instead of compounding yearly, we're going to compound it monthly. So 12 times 10 is 120. And if you want to try this on your calculator, you'll find that you end up with $1,647.01. So, okay, that was somewhat better. We made another $12 just by compounding it more often. And let's try it one more time. 10 years, but now let's compound it daily. So 1 plus 0.05 over 365 raised 3650. That's going to be $1,648.66. So get a big jump going to monthly, going to daily didn't help that much. We get another $1.50 out of it. If we were to switch to continuously, it's not much greater than this. It doesn't actually help that much. All right. Kernel of wisdom here is this formula, which you didn't have before now, and so you probably might have had trouble on the last problem on the homework. I apologize, I should have put it there. If you got it, all the better. a very practical problem. We're going to switch gears now. We're going to do something very mathematical and very abstract. We're going to look at something called Euler's constant. Euler's constant is a number. It's one of the most important numbers in mathematics. It's probably second only to pi. Right? Everybody knows pi and knows how important pi is. Euler's constant, we give the symbol, the script E. There are various ways you could come up with E. I'm going to show you probably the simplest one. We're going to take an expression from our compound interest formula, and we're going to take a look at it. We want to look at 1 plus 1 over n raised to the n. This would be equivalent to if I had $1 and I invested it at 100% for 1 year, but at different compounding rates. So, all right, let's take a look at the value here for various n. N is 1. Well, 1 plus 1 over 1 to the 1, that's just going to be 2. That's the only one I can do in my head. We go next to 10, and it comes out to about 2.59. Okay. It's larger than 2, but less than 3. Repeat this, we go make n 100. See what's happening? This is 1 plus a very small number, and we then multiply it by itself a lot of times. Right? So here we get 2.705. And let's just jump to 10,000. And we have 2.7184. You can kind of see it's starting to settle down now, right? It was 7.0, now it's just almost 7.2. And if we go to 1 million, this number is settled down to 5 decimal points, decimal places, 1.828. People who like to memorize the digits of pi, you don't hear people memorizing the digits of E very often, but which is too bad because they give you, the number gives you a little head start. If you can remember 2.71828, the next 4 digits are real easy. 1828. So as n gets very large, this approaches a number which, again, we call Euler's constant. It, like pi, is irrational. The decimal goes on randomly forever. But it's a very, again, it's a very important number in mathematics that we're going to run into in this class quite a bit. Need another column here, but see if I can squeeze it in. It turns out that if I enhance this expression to be 1 plus x over n to the n, then for any, when I increase n, for any x, what this is approaching is Euler's constant raised by the power of x. This is also, just like Euler's constant isn't very important, this is a very important function in mathematics. We'll see instances of that. Okay, so let's go back to compound interest here for a second. If I want to compound my interest now continuously, or some people will say infinitely, this just becomes my initial principal times e raised to the power of the interest rate times t. So already you can see E has kind of a purpose in life. Anybody have a scientific calculator here? Take a look at it. You see a button that says e to the x? Yeah. If you were wondering why that button is there, it's because it's a really important function. Millions and millions of scientific calculators have it on there. It must be important, right? All right, that's any questions? Compound interest, E for the moment. We're going to move on to another topic. Oh, yes. This is the, okay, so this function, pretty clear, right? It's a future principal given some starting principal, some interest rate, and some number of years, right? And where n is a number, it tells you how many times you compound it. 1 would be yearly, 12 would be monthly, right? But if you increase that n, just beyond, you know, to where you're compounding it not just every day, every minute, every second, nanosecond, right? You end up with this formula, which is just the initial principal, e raised to the interest rate times the number of years. Okay. Okay, we're going to switch gears a little here. As you'll see, we're not really leaving exponential functions behind, but we are going to go, we're going to be using them a lot in the next few minutes. But we're going to start a new topic, which is log functions. Anybody run into logs before? The log function? Yeah. They're confusing, aren't they? Anybody not confused by logs at all? I find logs confusing. Okay. Well, I can figure them out. Log functions. As if by magic, my pen just turned blue, green. It could happen to anyone. Okay. I know this is going to seem kind of hokey, but I want you to repeat after me. A log function is the inverse of an exponential function. A log function is the inverse of an exponential function. Okay, that was good. I'm going to do it one more time with a little enthusiasm. Right? A log function is the inverse of an exponential function. Log functions, confusing. Exponential functions, not so much. So So we want to keep that in mind while we're looking at what a log function is. All right, let's start with a very simple exponential function. F of x equals 2 to the x. Now, here we have 2 is the base, and x is the exponent. 2 is a little unusual base unless you're a computer science major. Then you will run into this as a base pretty often. And the inverse function is log to the base 2 of x. So this is the inverse function, this function. Now let's just look carefully what happened when we went from the function to the inverse function. Yeah, let's just leave it that way. So the base kind of crawls over here under the word log. And the exponent becomes the subject of the function. All right, that's still pretty confusing, but let's look at a real example here. I say f of 4, this is my function, that's just 2 to the 4, raised to the 4th power, which of course is 16. Now I'm going to look at my inverse function. My inverse function is going to take my 16, something in the range of this function, it's now the domain of this function. That's going to become log to the base 2 of 16, but that's going to become 4. Right? This function does something to 4, raises 2 to it. The inverse function, the log, takes that number and finds what exponent you would raise 2 to get it. It is confusing, but we're going to go over it a lot. You're going to have to do the homework. You're going to have to practice, because otherwise it's never going to become clear. Okay. Let's look at another example. Let's take a look at f of x equals 10 to the x. So the inverse function is the log to the base 10 of x. And again, we want to look at a real example here. We want to say, well, let's f of 3. That's 10 cubed is 1,000. So if I ask what the inverse function of 1,000 is, that's log to the base 10 of 1,000, which of course is equal to 3. In other words, I want to know, what do I raise 10 to get 1,000? The answer is 3. All right, let's try one that's a little more confusing. See if we have a handle on this. What is the inverse function of 0.001? That is the log to the base 10 of 0.001. What's that equal to? What do I raise 10 to get 1,000? John? -3. Oh, -3. Yeah, because 10 to the -3, right, is 1 over 10 cubed. It's 1 over 1,000. 0.00. function is the inverse of an exponential function. Everything you need to know about log functions, you could figure out knowing that one important thing. All right, let's do one more that's a little more difficult. Let's look at the log to the base 16 of 4. So what I mean is, if I have 16, see, I even get confused by this. If I have 16 to the x equals 4, what is x? I raise 16 to get 4.
Why not?
Okay, everybody, let that sink in. A half. Why is that a half? Well, really, I want to find the square root of 16, right? That's raising it to a half to get 4. So that's equal to a half. One little kind of aphorism along with my comment about it being an inverse is a log function is an exponent. This log function gives me an exponent, 16 to the 1/2. Something to keep in mind when you're trying to sort this out. All right. A word on notation. A few words on notation. We're gonna see a few different bases, right? We're gonna see log to the base 10. We're gonna see log to the base 2 on occasion. We're going to see this weird thing. We're going to see log to the base e. Remember e from like 5 minutes ago? Log to the base 10, called a common log, has a name. We used to use them a lot to do calculations before we had calculators. You'll see that you can use logs to avoid doing multiplication. They also help doing roots, cube roots, roots to the 5th, roots to any number. We don't do that as much anymore because we have a little scientific calculator at our hands that magically figures these things out for us. For reasons that I can't really explain at this time in your education, logs to the base e are called natural logs. To a mathematician, there's something about e that makes this a very natural log. We'll get a hint of it. The notation I want to talk to you about is, what does this mean? If you look on your calculator, what does it say there? Does it say log to the base 10? No, it doesn't. It just says log. So on your calculator, this is log to the base 10. If you're in a science class and you see log, it's going to mean log to the base 10. But if you take math and you take the next class after, say, calculus, maybe even calculus, this is going to mean log to the base e. Yes. However, scientists need to still use the natural log, so they give it their own name. Computer scientists will do this too. They'll call the natural log, they'll call it ln of x. What I want to be clear on is I intend never to use this expression because it's ambiguous. If I mean log to the base 10, I'll write log to the base 10. If I mean natural log, I'll either write log to the base e or ln of x. It's just a notational thing you should be aware of. Pretty sure if like you use a computer language, they're going to use this assumption, and they'll probably have an ln function. Okay. Let's take a look at what a log function actually looks like when you graph it. So take a minute to warm up. So I've put both the exponential function, 10 to the x over here, along with, see, I didn't intend to do that, but that's just what my graphing program did. This is log to the base 10 of x. And, well, of course, they're inverse functions, right? So, of course, the log function is just going to be a mirror across y equals x of the exponential function. That's what we'd expect, right, of an inverse function. Also, let's just look for a second at the domain and range. The domain of the exponential function is all reals, right? It's all along the x-axis here. And its range is just numbers greater than 0. So, of course, with the log function, we get the reverse. The domain, well, there's no log of 0 or log of a negative number. Those are undefined, just like dividing by 0 is undefined. But, so the domain is all numbers greater than 0. But the range, you'll see, is all reals. Now, that might not be perfectly clear, but if you look from 1 down, from 1 to 0, the function comes down asymptotically to the y-axis, so it's going to include all negative numbers. That's its range. And as it goes off in the x direction, it's increasing. It increases very slowly, but it does increase. And so eventually it catches all real numbers no matter how big. I think the other day I might have mentioned that, yes?
So can you what was the domain and range of each function?
The domain of the exponential function is all real numbers. And its range is y greater than 0. The log function is just the reverse. Its domain is x greater than 0, and its range is all real numbers. I think I said this the other day, that the exponential function increases faster than any polynomial function? Well, the reverse is true. The log function is going to increase slower than any polynomial function. Just a little factoid to know. Okay. In this class, we're going to do quite a bit of manipulation with logs. And so we need to know how to do that. We need to look at some properties of logs that are going to allow us to manipulate them. Eventually, we're going to solve equations with log functions in them. We're going to start out really simple here. And again, I'm going to try and always show you the exponential version first. Right? So if I say a to the 0 equals 1, that answers this question: what is the log to the base a of 1? Someone can just look at that and tell me. I have some a, I'm not even going to tell you what it is. But when I find the log to that base of 1, I always get what? 0. Elliot, right? I have this feeling in my head that I didn't mark you present. I apologize, Elliot. What's your last name?
W-A-L-D-D-O-G-E-L.
Good marking present. Okay, sorry. Okay, yeah, the log of to any base of 1 is 0 because any number to the 0 is 1. Right? Okay. A to the 1 is equal to a. That tells me that the log to the base a of a is always 1. Okay? Remember, this is an exponent, right? A to the 1 is a. A to the 0 is 1. Well, one step further, a to the x is, well, it's just a to the x. That's kind of simplistic. But if I look at the log to the base a of a to the x, right, I think of this here, what's that going to be? Log to the base a of a to the x. Yes?
It's X.
It's just x. There's another way to think about what I just wrote. Remembering that the function a to the x and its inverse is log to the base a of x. Remember this property of inverse functions? What's f of f inverse of x and f inverse of s of x? What are these both equal to? Now this should just snap into your mind. You have it etched on your palm. If I have a function, I operate on x, and I have an inverse function, and I operate on the result of that, what does the inverse function do? Yes?
We both get x.
Yeah, they're both x. I use the function to get to my range, and then I use the inverse function to get back the original x. That's what an inverse function is. And this is just a statement saying the inverse of an inverse function is the original function. Well, that's what I'm saying here, right? I've got two functions, a to the x and log to the base a of x. If I say log to the base a of x, what am I doing? I'm applying the inverse function to the function. So of course I get x. It is confusing when you, notation doesn't really help your mind, but okay. Here's the $10 question. What is a to the log to the base a of x equal to? I saw that hand go up. No? What am I doing here? I have a function a to the x. I'm sorry, I have a function log to the base a of x. I'm taking the result of that, the inverse function, plugging it into the original function. Right? That's what I was doing here. What do I get? Yes? You get x, yeah. These are two properties of log functions that come in very handy because they're inverse functions. Remember? Everything you need to know. All right. Let's keep going here. Let's take a look at a to the x plus y equals a to the x times what? Oh, it's hot. Makes one sleepy. One has to rise to the occasion. This is laws of exponents. We've been through these, right? What am I doing when I'm adding the exponents of a base?
Multiply.
Yeah, multiply. Times what? A to the y. Right. Okay. The equivalence statement using the inverse functions looks a little funny at first. You have to stare at it, you have to let it sink in. Log of x, y. Well, let me do it in the same order. Log of x plus log of y equals log of xy. Remember, logs are exponents, right? So if I'm adding exponents, I'm multiplying the numbers. This is really important. Similarly, a to the x minus y is a to the x what? Divided by y. Whoever said that? I couldn't tell. Congratulations. Thank you. Well, log x minus log y is just log of x divided by y. Okay. Here's where that use I mentioned earlier in science of using logs before we had calculators. See, we would have a, I'll show you, probably not today, but we would have a table of logs. We would take the two numbers we wanted to multiply, x and y. We would find their logs. We would add them. And then we would look up in a reverse way in the table what that value was. That would tell us what the product is. Same thing with division. So we can just do a lot of multiplying and dividing by adding and subtracting. Now that may not seem like such a big deal today because you have a calculator, but if you have some problem where you have to multiply a bunch of numbers, divide by a bunch of numbers, maybe find the square root, and all you have is pencil, paper, and a log table, it's a lot easier to use the logs. Okay, we're almost done with these properties. Let's take a look at a to the x, and let's raise it to some power. Square it. And that's equal to a to the what? I hope people are just sleepy. If you don't know these laws of exponents, you really need to review them. You really do. Yes? 2x. Well, let's see what this would mean on this side. Let's say I have log of x squared. Well, this tells me that that's log of x plus log of x, right? I want to multiply x times x, I just add the logs. But mathematically, that's just 2 log of x. What happened here? I have log of x squared, and 2 just gets put out front. So I can square a number now by multiplying the log times 2. This didn't have to be a 2. It could be some other number. It could be 4, 10. It could be half. I could find the square root this way. So this is a really, really powerful property of logs, really useful property. Let me write it as a property. Log to x to the a is equal to a log of x. Right. All right, let's look at a few problems we can solve using these properties. Let's start with log to the base 4 of 2 plus log to the base 4 of 30. So that's, according to my property, that's log to the base 4 of what? About 2 times 32. Okay. So now I want to think about what is log to the base 4 of 64. So I'm going to write it using the inverse function, right? What I mean is, this is x. 4 to the x equals 64. Okay. There's the base. This is the exponent. That's what a log is, an exponent. So looking at this, what's x equal to? 3. So the log to the base 4 of 64 is just 3. You want to get to where you don't need this intermediate step. You just look and say, oh, log to the base 4 of 64. Well, 4 cubed is 64, so this is 3. Okay, let's try another one. Log to the base 2 of 80 minus log to the base 2 of 5. So that's log to the base 2 of what? 80 divided by 5. Okay. What's 80 divided by 5?
16.
Everybody, you can do this in your head. 16, right? 5 into 8 once, 5 into 36. Okay, so now what's the log to the base 2 of 16? So 2 to what is equal to 16? 4. Good. All right, one more, like this. 1/3 log to the base 10 of 8 equals. Well, remember, I can take this factor of the log and make it the exponent. So this is log to the base 10 of 8 to the minus 1/3. Okay. It's 8 to the minus 1/3. So 8 to the 1/3 is 2. So 8 to the minus 1/3 is, didn't hear anybody clearly. Did someone say 1/2? Yeah, 1/2. So this is 10, log to the base 10 of 1/2. Now, there's no way I can just simplify that with my head, but someone out there has a calculator, so I'm going to punch in log of 1/2. So what do you get? -0.3. Okay, let's think about that for a second. Does that make sense? Right. Remember the log function looked like. Okay, so 1/2 is over here somewhere, right? So the log function is going to give me a negative number, right? The bigger the negative number, the smaller the value, right? Okay. We might not be so lucky as to have numbers. We might have a more complicated algebraic expression. So let's take a look at take a look at this one. 3 log x plus 1/2 log of x plus 1. And we want to simplify that. But really what I mean in this context by simplify is just one log function containing everything. So this becomes log of x cubed. This becomes log of x plus 1 to the 1/2, which is just the square root. And now I'm adding these logs, so this is just going to be log of x cubed times the square root of x plus 1. Take a look at one more of these. 3 natural log of s plus 1/2 natural log of t minus 4 times the natural log of t squared plus 1. So again, I want to combine that. I want to get everything so there's just one log function. So again, log of 3 log of s is the log of s cubed. Half log of t is the log of t to the 1/2, or square root of t, and minus 4 times the log of t squared plus 1, that's the log of t squared plus 1/4. But now I want to combine these, right? Adding logs is multiplying, subtracting logs is dividing. So this just becomes the log of square root of t s cubed divided by t squared plus 1/4. So that's kind of how you manipulate these expressions. We're going to stop here and we're going to look at this some more on Friday.